In this video, we talk about how to represent the signed integer number. So the conversion we have so far represented have involved only the unsigned number. So in order to represent signed integer, computer system allocate the high order bit to indicate the sign of a number. So the high order bit is the leftmost bit, and that's also called the most significant bit. And 0 is used to indicate the positive number, and 1 indicate a negative number. So the remaining bits contain the value of the number, but it also can be interpreted a different way. Okay, we can see later on in a few examples. There are three ways in which the signed binary integer may be expressed. The signed magnitude, 1 complement, 2 complement. So we're gonna show each of them one by one. Okay. So for example, in an 8-bit word, the signed magnitude representation places the absolute value of the number in the 7-bit to the right of the signed bit. So here's an example. We have the 8-bit signed magnitude representation. So for example, the positive 3, the most significant bit right here represent the positive sign, that's a 0, and the remaining 7 bits right here are gonna be represent the value of 3. So 3 represent by string 1 1 right here. Okay. On the other hand, for the negative 3, the first most significant bit right here, that's gonna be 1, because 1 to represent the negative sign, and the remaining 7 bits right here represent the value of 3. Okay, so that's gonna be represented by 1 1 right here. So a computer perform arithmetic operation on a signed magnitude number in much the same way as the human carry out the pencil and paper arithmetic. So human often ignore the sign of the operands while performing a calculation, and then we apply the appropriate sign after calculation is complete. In order to do the calculation, we will first learn some basic rule of binary addition. So here's the four simple rule. In binary addition, we have 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 1 0. Okay, this is 1 0. Remember, this is the binary representation. 1 0 is not 10. Okay, 10 is the in decimal representation, but this one is a 1 0. Okay. The simplicity of this system makes it possible for digital circuit to carry out arithmetic operation, and we will describe the circuit in chapter number 3 in next week. And so let's see how the addition rule work with the signed magnitude number. So here's an example. We want to compute the signed magnitude binary arithmetic of the sum of 75 and 46. So in order to compute the sum of 75 and 46, the first step is that we convert 75 and 46 to binary and arrange the sum as a separate positive number, and as we do with the decimal. So basically here the binary string of the 75, and here's the binary of the 46. So we just stack them up and do the addition calculation. So how can we do the add the sum of the choose number 75 and 46 using signed magnitude representation? So we have the 0 0 right here, that's the sign of the two positive numbers. So we have the two number 0 right here, that's the sign, and here the so we just do the addition the same way we do the addition in decimal arithmetic. Okay, so we have the 1 plus 0 equals to 1. Okay, that we're gonna do from the right from the right to the left. Okay, so the first digit 1 plus 0 equal 1. Now we do 1 plus 1 equal to 1 0, so we write down 0 and 1 we carry to the next digit. So we have a 0 plus 1 equal 1, and now we plus 1 equal to 1 0, so that we're gonna have the same. So we write out 0 and we carry 1 to the next digit, so we have this 1 plus 1 and then plus 1 equal 1 1, so we write out 1 and we carry 1 to the next digit. So we have the 1 plus 0 equal to 1, and we have nothing to carry to the next digit, so the next digit was 0 plus 1 equal to 1, and 1 plus 0 equal 1. Okay, so this is a value, we add them together, so we have the new binary string right here, that the sum of the 75 plus 46. So once you get this one, we just have the side right here, just 0 and 0, so we write out 0 for the result. So in this example, we were careful to pick two values whose sum would fit into the 7-bit. So if this is not the case, so we may have problems. So let's see what kind of problem we can have. So now assume we want to use sign magnitude binary arithmetic to compute the sum of 107 with the 46. So we can see that the sign also 0 right here, just represent the positive side of 107 and also 46. So this is the sign. And the first binary string right here, that's the string of the 107, and the second string right here, that's 46. So all the calculations are the same as before. So we have the 1 plus 0 equal to 1, 1 plus 1 equal to 1 0. So we write out 0 and carry 1. So 1 plus 0 plus 1 equal to 1 0. We write out 0 and carry 1. So 1 plus 1 plus 1 equal to 1 1. We write out 1 and carry 1. And 1 plus 0 equal to 1. 1 plus 1 equal to 1 0. We write out 0 and carry 1. So 1 plus 1 plus 0 equal to 1 0. We write down 0 and carry 1. Okay, so we can see that carry from the 7-bit, that's gonna be overflow and is discarded, giving us the erroneous result 107 plus 46 gonna equal to 25. Okay, that's the 25 because the side right here is just add together, so just combine together, we have the 0, but the carry out bit of the last operation right here just got discarded, so this one is we return a erroneous result. So the sign in sign magnitude representation just work just like in the pencil and paper arithmetic. So for example, using a sign magnitude binary arithmetic, we try to compute the sum of negative 46 and negative 25. So the negative can be represented by the bit 1 right here for both of the number, and this binary string right here just represent the value of 46, and the binary string right here the value of 25. Okay, so the first step to compute the sum of two negative numbers, we just do the calculate the sum of two value. So basically we do the same. 0 plus 1 equal 1, 0 plus 1 plus 0 equal 1, 1 plus 1 0 equal 1, 1 plus 1 equal 1 0, we write down 0 and carry 1, so 1 0 1 equal to 1 0, write down 0 and carry 1, so 1 1 0 equal to 1 0, write down 0 and carry 1, so we have the 1 0 0 equal 1. Okay, the sign right here, we have the both of them negative, so we just combine, we get the negative sign right here, so that's the way we do the sum of two negative number. And so that's the same, that's just the same way we do with add and the number and the supply the negative sign when we are done with the number. So what about the mix of the sign addition or subtraction is done in for easy can be performed for the sign magnitude. So basically it's gonna be done the same way. For example, we want to use the sign magnitude representation to compute the sum of 46 and negative 25. Okay, so the first number right here, that's the with sign equals 0, that's the positive sign for 46, and this is a binary representation of 46. And the second number right here, we have the that's the 25 right here, and the 1 right here just represent the negative side of 25. Okay, so the side of the so in order to compute the sum of these two numbers, so basically we do the same way as we perform using the paper and pencil. So this number subtract this number, so basically because 0 cannot subtract 1, so we carry we borrow 1 from here, and that's equal to 2 in this digit. So we have the 2 subtract 1 equal to 1. Okay, when we borrow 1 right here and we can return 1, so 1 subtract 1 equal to 0. Okay, so the next one, 1 subtract 1 equal to 1, 1 subtract 1 equals 0, and again right here 0 cannot subtract 1, so we borrow 1 from here, so we got the 1 from the higher position right here corresponding to the value of 2 in the lower position here. So 2 subtract 1 equal to 1, and then we return 1, that's the so 1 already borrowed, so this one equal to 0, and this column equals 0. Okay, so basically this string subtract this string equal to this string, and the sign of the result gonna be get the sign of the number that's the with the larger value. So basically 46 larger one this one, so the sign gonna be a copy from this side the number with larger value right here. Okay. So we can see that sign magnitude representation is easy for people to understand, but also it requires a complicated computer hardware. Also, another disadvantage that the sign magnitude is that it's allowed to a different representation for a 0. So we basically have the positive 0 and negative 0 that represent the same number 0. And for this reason and many other reasons as well, the computer system employ a different way to represent number that we call a complement system for numeric value representation. And the next video we're gonna show how the number will be represented by using the complement system.